Alright, so in this video I'm gonna be explaining this important article with the title Towards Deeper Graph Neural Networks with Differentiable Group Normalization. This paper in NeurIPS 2020. So graph neural networks which learn representation of a node by aggregating its neighbors have become an effective tool. But oversmoothing is one of the key issues which limit the performance of GNNs as the number of layers increases. We should distinguish these things. Underreaching is very different from oversquashing. They are very different from oversmoothing, overfitting, overcorrelation. These should be decoupled. They are very different concepts that occur when you want to have a deeper graph neural networks with these traditional message passings. So oversmoothing, it is because the stacked aggregators would make node representations converge to indistinguishable vectors. You cannot distinguish two nearby nodes. And several attempts have been made to tackle the issue by bringing linked node pairs close and unlinked pairs distinct. However, they often ignore intrinsic community structures. The topology, and would result in suboptimal performance. The representations of nodes within the same community class need be similar to facilitate the classification, while different classes are expected to be separated in embedding space. So they introduce two oversmoothing metrics, differential group normalization, for example, and a novel technique which is called differential group normalization. It normalizes nodes within the same group independently to increase their smoothness. One group, two group, so it normalizes and separates node distributions among different groups to significantly alleviate the oversmoothing issue. So most of the literature is oversmoothing on node pair distances. They forget the group structures. So they have these group normalization to significantly alleviate oversmoothing. So we have aggregation and update. Some people say combine. So with different aggregation and combinations, we have different graph neural networks. But in GNNs, the neighborhood aggregation strategy smooth nodes representations over a graph. It will make the representations of nodes converge to similar vectors as the number of layers increases. However, oversmoothing is also highly related to global graph structures, which have not been taken into consideration. For some unlinked node pairs, we would need their representations to be close if they locate in the same community. For example, in community detection, these two nodes that belong to the same community, we want to have similar representations. Similarly for others. But we want this representation of this node and this node to be very different because they are from different communities. Thus, we propose two novel oversmoothing metrics, group distance ratio and instance information gain. they quantified over smoothing from global and local views. So this is the R group. This group distance ratio measures the ratio of intergroup distance over intragroup distance. Okay, if this is an algorithm, how does our brain creating such a regularization? So you see, we do many things which is not natural in machine learning because we cannot simulate it in our brains. Our brains are more sophisticated. Of course, they have simple rules, but it provides complexity out of very simple message passing rules. So if they belong, HIV belongs to L sub I as a labeled group, or HIV and HIV prime belong to L sub I. This is the measures the ratio of intergroup distance over intragroup distance. Intergroup is this one, and intragroup is this one. So in an attributed network, a node's feature decides class to be to some extent. We treat each node instance independently and define instance information gain as how much input in feature information is contained in the final representation. We define their probability distributions P sub x and P sub h and their joint distribution. So G measures the dependency between node features and representation via their mutual information. So this is a random variable of input feature, and H is the random variable of representation. I think it was in the previous video that I was talking about this X, H, Y, that we want to minimize the mutual information between X and H and maximize the mutual information between H and Y. So this is in the same spirit. So based on KDE approach, a lower bound of mutual information between input feature and representation vector can be calculated. But it is lower bounded by this one, and that's why we can calculate it, because this is simple to calculate. So we start with graph regularized optimization problem. To optimize over smoothing metrics of G and R, one traditional is to minimize this loss function. But there is group normalization that the ith column of S indicates assignment probabilities of nodes in graph to ith group. Oh, this reminds me the assignment, cluster assignment in hierarchical graph pooling. You see, all of them are with the same spirit. And using that, we go from H to H, we get the H sub I, and then we cluster and normalize nodes in each group. Of course, in hierarchical graph pooling, we don't have this normalization, so you can write a paper and talk about this. because this part is very important. The left part in the above equation represents the soft node clustering for group I, whose embedding matrix is given by H sub I. The right part performs a standard normalization operation. In particular, mu sub I and sigma sub I denote the vectors of running mean and standard deviation of group I. Okay, then DGN generates the final embedding for the next layer like this. Summation is over the group elements. And the group normalization rescales the node embedding within each group independently to make them similar. And this is differentiable clustering. We apply a linear model to compute cluster assignment matrix S using this softmax of H times U. So as the number of layers increases, you see the accuracy. But for graph attention, the accuracy is going down. So we may say that GCN is more robust to increasing number of layers. You see the group version is almost similar to just the batch version. So not a big marginal gain. So they have these important data sets, Cora, PubMed, and they have different layers. Batch normalization, and you can see the accuracy. This is the optimal layers. So the optimal layer numbers, which gives the highest performance. So now sometimes a big number, sometimes very small number, sometimes intermediate for PubMed. So layer 30 out of 120, layers 15, layers 2. This PubMed 19,000, it has 19,000 nodes. So it has more nodes, and so therefore more edges. Classes only 3. But the co-authors class is 15.